I'll start by describing some now basic properties of Fano varieties. So this is by Birkar, Kashini, Haken, McKernan. They showed that for any Fano variety, which could be smooth or more generally KLT, and well, also for Fano pairs, but I won't care about that in this talk, then the Cox ring of X is finally generated. Which means the direct sum of the space of sections of all line bundles on X. Oh, let's say over the complex numbers, say. Then this ring is finally generated over C. Right, so there's some minor detail here that this doesn't quite make sense because an element of pick is an isomorphism class of line bundles. It's not exactly a line bundle, but you can make sense of this by picking generators for this group and picking actual line bundles which generate this group, and then this is a well-defined ring. And in any case, it's a well-defined ring up to isomorphism. Right, so now I'll just make the point that this is an interesting statement if X has Picard number greater than 1. I mean, if X has Picard number 1, then this is kind of obvious, which are maybe, Picard number 1 is maybe the most interesting kind of Fano varieties anyway, but in any case, this is an interesting statement for Fano varieties with Picard number bigger than 1. Why is it obvious for X with Picard number 1? Because then line bundles, if Picard group has rank 1, then this is just sum of sections of some ample line bundle plus multiples of that. And if you take any projective variety and take sections of an ample line bundle and powers of that, you get a finally generated ring. That's basically just the coordinate ring of X embedded in projective space. But if you take a line bundle on some general projective variety that's not ample, then if you look at sections of L and its powers, that's usually, or in general, not a finally generated ring. But this is saying that for Fano varieties, so just to write that again, it means that minus k is ample. For Fano varieties, for example, smooth ones, you can take any line bundle you want, and sections of its powers give you a finally generated ring. Let's see, what can I do here? And even if you put together all line bundles at the same time, you get a finally generated ring. Okay. So there's a more geometric way to formulate this by Hu and Kiel. So this is a much more elementary result. So it described what it means for any projective variety to have finally generated Cox ring. So in other words, if you have some projective variety where this ring is finally generated, what does that tell you about X in geometric terms? Okay, well, there goes. So it's kind of a long equivalence. So Hu and Kiel showed the Cox ring is finally generated if and only if. So the Neff cone of X is rational polyhedral. And Neff is equal to semi-ample. So every Neff divisor is semi-ample, meaning that the base locus, so Neff I've defined, and semi-ample means that the base locus of some high multiple of that is empty. yeah, saying that the Neff cone is, sorry, saying that every Neff divisor is semi-ample is saying that every point in this Neff cone gives you a contraction of x, because the whole point of semi-ample line bundles is that by taking powers of, by taking prods, I guess, of the section ring of a semi-ample line bundle, you get some other variety that x maps onto. So it's equivalent to saying that every face of the cone of curves can be contracted. So this sentence is not yet finished, but the Cox ring finally generally means that these properties hold plus some more. I just want to make the point that these properties for Fano varieties were already known in the 80s, right? Because these are exactly what the cone theorem tells you about Fano varieties. The Neff cone is rational polyhedral, and every face of the cone of curves can be contracted. Oh yeah, and one more point, that for a surface, for x of dimension 2, the sentence ends here. These conditions, this is exactly what finite generation of the Cox ring means for surfaces. But in higher dimensions, you have to say more. Right, so here goes. X has only finitely many modifications, which I'll define in a second. So say that for this talk anyway, a modification of a projective variety x is some other q factorial projective variety y. I don't quite know, but maybe I wanted to assume q factorial there. I'm not sure. Probably doesn't matter. Anyway, a q factorial. So I'm imagining x as being a q factorial projective variety here. And then a modification of that means some other q factorial projective variety y with a birational map. So y comes with a birational map to x. And I want that birational map to be an isomorphism in codimension 1. That is, this map F is an isomorphism from x minus some subset of codimension at least 2 to to y minus some subset of codimension at least 2. Okay. All right. So modifications don't exist in dimension 2, or in other words, a modification of x is just x. Again, x is a surface. All you can do with the surface is the only birational maps are something like blowing up a point, and then you replace a point by a curve which has codimension 1 in a surface. But in dimensions at least 3, there are non-trivial modifications, like what are called flips, flops, and so on, thanks to Miles. And I'll write down some examples of flips and flops later. So anyway, there are some, varieties of dimension at least 3 have some modifications, but if x is going to have finally generated Cox ring, it should have only finally many modifications. And each modification of x should also satisfy these first two properties here. So let's see. 1 and 2. So maybe this is 1 and this is 2. Okay, so not only x itself, but all of its modifications have rational polyhedral Neff cone, and every Neff divisor is semi-ample. And I think I would like to have one last bit of this sentence. Finally, every movable divisor on x becomes Neff on some modification. So where, so I'll expand on this in a second. x1 through xr, are the various modifications of x. Okay, so that's finally the end of that sentence, and let me just define the words there. So definition, a divisor D on projective variety x is movable if its base locus has codimension at least 2. Codimension at least 2 in x. So that means, so first of all, D is linearly equivalent to some effective divisor, and this means the intersection of all the effective divisors that are linearly equivalent to D. Right, so this is saying that there's no there's no codimension 1 subvariety that's contained in all the divisors linearly equivalent to D. Or in other words, yeah, L has, the corresponding line bundle has enough sections that they don't all vanish on some codimension 1 subvariety. Okay, let me see. Okay, so this is a useful notion when you're talking about modifications because, yes, I should mention that if you modify some variety, then you don't change the group of divisors on there, say V divisors. So let's see. Note that if x, say if y is a modification of x, then let's say the set of codimension 1 subvarieties of x is exactly the same thing as the set of codimension 1 subvarieties of y. You're not changing anything in codimension 1. And also, linear equivalence on x is the same thing as linear equivalence on y. So, yeah, so also, if you look at these neurons invariant groups, they are just the same. And another nice feature of that is that the space of sections of a line bundle on x is exactly the same as the space of sections of the corresponding line bundle on y. I mean, a bit sloppy. L might be only Q Cartier, but let's see. So moreover, for any V divisor D on x, space of sections of D on x is exactly the same thing as the space of sections of the corresponding divisor on y, just because, I mean, these are normal varieties. That's part of what I mean by Q factorial. And, you know, so to have a section of a line bundle on a normal variety, it just means they have a rational section that doesn't have any poles on any codimension 1 subvarieties. X and Y have the same codimension 1 subvarieties, so you have that identification. Right. So in particular, 2 modifications have the same Cox ring. Equals, really. Okay. And, yeah. So if you compare a divisor on x and y, it might have a different base locus on x than different looking base locus on x than it does on y, but you're obviously only going to change the base locus in codimension at least 2. So, a divisor is movable on x if and only if it's movable on y. Oh, this terminology didn't get defined. So this just means, for me, let's say the closed, because I like closed convex cones, say the closed convex cone spanned by movable divisors. Yeah, because just divisor on y, you got a movable divisor on x. The corresponding divisor on y has the same space of sections. If it was movable on x, it's obviously movable on y. If it was base point free on x, it might not be base point free on y, but movable, yes. So how does this work? Okay, we have the Neff cone of a projective variety contained in the movable cone, just because, at least in the interior of the Neff cone, you've got ample line bundles, And an ample n I mean, some multiple of it is obviously movable. So you've got, if you have some modification of a variety, then nef cone of x and nef cone of y both sit inside the same bigger cone, the movable cone of x. So here's maybe an f of x, and here's perhaps an f of y. And the picture is always more or less like I draw there, in the sense that if you have a non-trivial modification of some variety, then these nef cones are actually different, and in fact, they can meet at most on their boundaries. So the interior of the nef cone of x doesn't meet the interior of the nef cone of y. Okay, which is obvious because this means you can't have a divisor that's ample on x and simultaneously ample on y. Why is that? Well, if you have an ample divisor on some projective variety, then, so to speak, you could reconstruct the variety from the divisor, more precisely from the ring of sections of that divisor. Right? You just take, given an ample divisor, proj of the ring of sections of that divisor is the projective variety. So, you know, if you had some divisor that's ample on x and also ample on y, I mean, the ring of sections of D is the same on x and on y, so that would tell you that, you know, proj of that ring, which is x, is the same thing as proj of this ring, which is y. So, so that proves this, and in particular, yeah. So different nef cones, their interiors don't meet, and even though they all live in the same cone, the movable cone of x. Yeah. So anyway, that's what's sort of going on in this picture. Right. In general, a projective variety will have various modifications. Its nef cones will sit inside the movable cone of x, but they might not fill up the whole movable cone of x. However, that does happen when the Cox ring is finally generated. Okay, so you can interpret BCHM's theorem there as telling you that Fano varieties have all these happy properties. Okay. All right. And the point of this talk is to study how these properties change when you deform a Fano variety. So I just state this theorem by Pernay and Aiken. Yeah, this is about a sort of more specific class of Fano varieties. So let x not be a q factorial terminal Fano variety. Oh, I guess maybe I'll quickly write down the definition of terminal. Right, terminal singularities come up naturally in the minimal model program because this is what you get as the output of the minimal model program starting from, say, a smooth variety. Okay, so what they propose to consider is, suppose you have a family of which this is one member. Let this be a flat projective morphism. Say it's a one-parameter family, so B is, let's say, a smooth curve. Say 0 is the name of a point in that curve, and x naught is fiber over that point. So I assume I've got a family of varieties where one fiber is the q factorial terminal Fano variety. I did say flat, yes. So then they showed that the Cox rings of these various fibers, they form a flat family if you formulate it. Let me formulate it a bit vaguely like that. Let's see, the rings form a flat family over a neighborhood of 0 in this curve. So, I mean, an algebraic way to say that is that you can, making some choices, you can write down a flat O of B algebra, a flat algebra over the ring of functions on B. If B is, say, an affine curve, you can write down a flat algebra over the ring of functions on that curve whose such that when you tensor it with C associated to any given point in B, you get the Cox rings of these different varieties. And what that means more concretely, because this is some kind of multi-graded ring, obviously, that just means that the dimensions of the pieces of that ring don't change as you move in the family. So equivalently, sort of the dimension of space of sections of some line bundle, maybe I should call it a Vey divisor, to be honest, is equal to the space of sections of the Vey divisor. It has the same dimension as the space of sections for any t near 0. D equals any Vey divisor on x naught. Yeah, I guess there's one slight detail there. I should just add, for that to really make sense, I should say that the divisor class group also doesn't change in a family. So sort of the group of Vey divisors is the same for all the different. Why is it? Sorry.
Why this? Maybe I did not understand.
Yeah.
Why it is sufficient to say that every piece is isomorphic to the other? There are relations in the box.
There are relations, but the definition of flatness, to say that one algebra is flat over another, it just means that the second algebra is flat as a module over the other. So it just means, it's just a condition on these rings. If you have graded rings, a flat family, flatness just means that those dimensions don't change. I mean, it's just a condition. Yeah. So, okay. Right. I mean, saying that sort of each of these, imagine that saying that each of these graded pieces of the Cox ring is a vector bundle over B. It's a, it's a coherent sheaf whose fiber have the same dimension everywhere. In other words, it's locally free as a O of B module. Okay. Yes. Okay. So here, to clarify this, so they also show something which is kind of implicit in my statement that the group of Vey divisors modular equivalence on X is the same thing as the divisor class group of XT for t near 0 under those assumptions. For exotic Q factorial terminal Fano variety. So the Cox ring, it's graded over the same group for all these nearby fibers, and the dimension of each piece in the graded group is the same for all the nearby fibers. Okay, so that implies that various properties of x naught are sort of the same as properties of these nearby fibers. So, for example, the effective cone of x naught, the effective cone of xt is constant for t near 0. So these things are living in these different vector spaces, but you can canonically identify these fibers. This is just basically it's something in topology. It's a certain homology group of x naught, and these homology groups are just you can canonically identify them for nearby fibers. So it makes sense to say that the effective cones of these various Fano varieties are literally the same. They live in essentially the same group, and they're not changing as you move in the family. Okay, I mean, this is obvious because the divisor being effective, it's just telling you whether or not x naught is 0. So this immediately follows from their theorem, and they also show they also deduce from the theorem that the movable cone doesn't change. So the movable cone is also constant for t near 0 under their assumption. I mean, that's maybe not so obvious, but they also deduce that. Let's see. Okay, so then they ask, so this stuff here says that for a Fano variety, a lot of its geometric properties are encoded in this sort of combinatorial data of, first of all, a rational polyhedral cone, the movable cone, and then a decomposition of that into finally many chambers, which are the Neff cones of the variety and its various modifications. So if the movable cones are staying constant, it makes sense to ask, is that decomposition also staying constant? So the question by Dufresne and Haken was, is the chamber, so under those same assumptions, is the chamber decomposition of the movable cone also constant? For t near 0. So you take a q factorial terminal Fano variety, deform it a bit. The movable cone doesn't change when you deform it, but does the decomposition there change when you move your variety? Okay. Well, that's certainly true for Fano varieties of dimension 2, because for Fano varieties of dimension 2, nothing is really happening in this decomposition. The movable cone of the surface just is the Neff cone. So this, this decomposition just has one piece, and so there's nothing to say. So yes, trivially for dimension of x equals 2. Although if you think of that another way, it's saying something interesting. I mean, so that's saying that for del Pezzo surfaces, the Neff cone doesn't change when you deform it, or in other words, if you take the dual cones, the cone of curves don't change when you deform a Fano surface. Let's see, smooth, I guess in this case, Fano surfaces xt. Okay, so this is something that's well known, but still a nice fact. The cone of curves is, for most Fano surfaces, spanned by the finally many -1 curves, and this is saying that sort of the set of -1 curves doesn't change as you move from one cubic surface to another or whatever. I mean, the -1 curves may sort of move around in a continuous way, but the number of -1 curves and their homology classes kind of stays constant. You might want to say sort of locally constant or something. You can have some sort of monodromy where the -1 curves switch around, but I'm just sort of asking what's happening locally here. Okay. Okay. So what can you say about this? Okay. So let's say in particular, this conjecture would imply that the Neff cone of a Fano variety is constant as you deform it. Just to emphasize, for a family where x naught is a q factorial terminal Fano variety. Okay. Right, so that's sort of the most concrete part of this question. And about this, some things are known. So let me say what is known. So theorem by Dufresne and Haken is that answer to the question is yes, sort of not just for the Neff cone, but the whole decomposition stays constant in dimension 3. So question or let me write this out in more detail. So the chamber decomposition of the movable cone, in particular the Neff cone, stays constant for t near 0 if x naught has dimension at most 3. Okay, so for dimension 2, this was kind of easy from their other results, but also in dimension 3 they get this. And the other major piece of evidence for this was that by Wisniewski we know that the Neff cone is constant for smooth Fano varieties of any dimension. So for x naught a smooth Fano of any dimension, the Neff cone, if you deform a smooth Fano variety a little bit, the Neff cone doesn't change. Okay. Which, is kind of an ideal, or equivalently, that's saying that the cone of curves of a smooth fauna variety of any dimension doesn't change. So it's a nice generalization of this fact about -1 curves on a del Pezzo surface. Okay. All right. Okay. So we should say something brief about the proofs of some of the stuff, like Vishnevsky's theorem uses, how does this work? He uses this smoothness assumption in several different ways. Let me think. Like, for one thing, he's using properties of the topology of smooth projective varieties, like the Hard-Lefschetz theorem. And maybe that you could hope to generalize to singular varieties. There are some versions of that for singular varieties. But then he's also using properties of deformation theory of rational curves, which kind of obviously works better on smooth varieties. So like he's sort of thing he's using are these dimension estimates that say, like, if you have a flipping contraction of a smooth projective variety, so you contract a k-negative, make a k-negative contraction, say you contract some subvariety to a point, then such a contraction has to contract a subvariety of dimension at least half the dimension of the whole variety. And so, for example, that says that there are no flipping contractions of a smooth threefold, because, flipping contraction of a smooth threefold meaning you contract a curve to a point, and that doesn't have dimension more than half the dimension of the variety. Whereas we know that for singular threefolds there are flipping contractions. So, so his argument definitely is using smoothness in a way that doesn't easily generalize. But still, nonetheless, that's some kind of evidence for the conjecture. But then I found that the answer is no. So I don't know, theorem, something that. So the answer, let's see, there are Q factorial terminal Fano varieties x naught of dimension 4. That deformations of them over a smooth curve, so that Neff cone of x naught is proper subset of the Neff cone of these general fibers. Okay. Okay. And let's see. So it's just to give some detail. So here, these general fibers are isomorphic to p floor blown up along a line, and the singular fiber, well, it has some singularity of index 2. Let me see. I think it's sort of more interesting to try to describe how to find this example rather than to write all the details of this thing. It's on the archive anyway. Let me see. So how do you look for an example like that? Okay. Yeah.
So Vishnevsky example, Vishnevsky theorem, the total space was smooth?
Well, yes, because I'm considering a flat family over. If one fiber is smooth, then an open neighborhood of that is definitely smooth. Yes. Yeah, it's okay. Yeah. Okay. Okay. So, right. All right. So, how do you look for an example like this? Okay, I had the following idea. So the idea was to right. So how can I say this? The idea came from the fact that one way to try to prove this thing would be to prove what's called the so-called volume criterion for ampleness for Fano varieties. But this criterion was already known not to be true for some other varieties, not like holomorphic symplectic manifolds. And so if I analyze what goes wrong in the case of holomorphic symplectic manifolds, that sort of suggested how to find something that goes wrong for Fano varieties. So let me say a word about this. Okay, so let's say that a projective variety X satisfies the volume criterion for ampleness if every line bundle that sort of looks like it's ample in a certain way actually is line bundle. It actually is ample. So if every line bundle L such that the volume of L, let's say the volume of L prime is equal to, I should call this something else. Volume of M is equal to M to the n, the intersection number of M with itself n times, n is the dimension. Every line bundle such that this holds for all M in this vector space of divisors near L is ample. Yes. Okay, so I have to define the words in there. So definition is that the volume of a line bundle means something like the limb soup, maybe, anyway, of the space of sections of big multiples of L divided by what should be the right power, so something like m to the n. And I think I want this times n factorial. Yeah, so you look at the asymptotics of how fast sections of multiples of L grow, the point being that if L is ample, then just by Riemann-Roch, then the volume of L is just given by the top intersection form of L. Okay. So then I hope this makes sense. So if a line bundle is ample, then, sorry. If this holds blah, blah, blah for all m and x near, in some neighborhood of L, then I want to conclude that L is ample. I'm sorry? Yeah, sorry that I screwed up that statement. So you see the point. If L is ample, then all the line bundles near L are also ample, and therefore they satisfy this equality. So you say that X satisfies the volume criterion for ampleness, so every line bundle that, satisfies this condition is actually ample. The point being, it would be kind of unreasonable to just say, to expect that every line bundle with volume of L equal to L to the n to be ample. That would almost never be true. Like there would be lots of line bundles where L to the n happens to be 0, and also L is very far from being ample, so its volume is 0. But if this holds for not only L, but for all line bundles near L, I mean, all the line bundles near L, some of them are definitely going to have this number being non-zero, and if these two things match up perfectly, you kind of think that L should be ample. Okay. All right. However, also, what's known about that? I guess Lazarsfeld studied this condition in his book, I suppose, on positivity. So what's known about that is that if X is say a toric variety, then X satisfies this volume criterion for ampleness. But not every projective variety satisfies that. Namely, holomorphic symplectic manifolds typically don't. Let's see. Sorry, volume criterion for ampleness. Okay, and why not? Well, it's because of the so-called Mukai flip, Mukai flop, rather. Okay, so this is following thing. So if you have a holomorphic symplectic, let's say fourfold. Suppose it contains a P2, that will automatically be Lagrangian with respect to the 2 form. And the normal bundle to this P2 will automatically be the cotangent bundle of P2, just because that's the way holomorphic symplectic manifolds work. And in that case, okay, there is a modification x naught to y naught that sort of cuts out this P2 and replaces it by another P2. So one way to describe it would be you take P2 and you blow up the P2, sorry, take x naught, blow up the P2. Inside there you would have, mapping to P2, you'd have the flag manifold of lines and planes in C3. And that can project down to P2 in 2 different ways. So that gives you, with some work perhaps, that gives you a contraction of x tilde where you contract this flag manifold down to P2 the other way. And this other variety is also smooth and holomorphic symplectic. Okay, and in this situation, what can I say? So if you take L to be an ample line bundle on y naught, then look at the corresponding line bundle on x naught. This is a modification because we're only changing things in codimension 2. Then L is not ample on x naught, but it looks ample from the point of view of the volume criterion for ampleness. Okay, so why is that? Well, the volume of L, how many sections L has, is sort of just the same on x naught as on y naught. So the thing that's making this L appear to be ample is the fact that I claim intersection numbers of divisors on x naught are exactly the same as intersection numbers of divisors on y naught. So because the intersection form on divisors on x naught is the same as that on y naught. So the vector space of divisors are canonically identified for these two spaces, but in general, when you make a modification, like if you make a flop or a flip of threefolds, then you usually change the intersection form on divisors. In fact, you might think that you have to do that. I mean, if you're sort of messing up some variety in codimension at least 2, you think you'd have to be changing the way divisors are intersecting each other. But in some sense, that's not true. Here's a flop of 4 folds. It doesn't change the intersection form. And why doesn't it change the intersection form? I was just claiming that there, but why doesn't it change the intersection form? Well, it's well known to some people in the audience. It's because epsilon and y naught, these two smooth varieties are deformation equivalent to each other in this case. So indeed, there is a smooth family of smooth holomorphic symplectic varieties, 4 folds over a smooth curve B that contains x naught. So x mapping to, I don't know, smooth curve, maybe you can take it to be A1, I forget, where one fiber is x naught. And you can make another similar family that contains y naught over the same base. This has dimension 4, this has dimension 5, therefore. And these two families are actually the same outside this special fiber. So there's the rational map between these two families, which is iso over V minus this one interesting point in the middle there. So, I mean, yeah, and it's this birational map is the given birational map from x naught to y naught on the special fiber. So we're just sort of changing a P2 there to, I mean, this birational map fails to be defined only on this P2 and in the other direction on that P2.
Sorry, there is something I don't understand.
Yeah.
I don't understand if the ampleness is a numerical condition, so I don't understand how it is possible that if the intersection form is the same, it's possible that
Right.
L is lump there and not there.
Right. It's subtle, I agree. It's a numerical condition in the sense that it depends on how a divisor pairs with curves. But sort of this identification, I mean, it doesn't identify curves in x naught in any obvious way with curves on y naught, you know? Yeah. Okay.
This is the obvious result.
What?
This is the volume correctly obvious result.
I think it probably is, yeah, right. Okay, but yeah, when you get high enough dimension, you can have this phenomenon, and so obviously, I mean, I should, you know, so this makes it obvious, I claim, that x naught and y naught have the same intersection form because x naught has the same intersection form as, say, xt here, and x sub t is just the same thing as y sub t for t not equal to 0 in this curve. You know, so intersection form here is the same as there. That's the same variety as this. That's the same as the intersection form here. Okay, so oh yeah, so another result Dufresne and Haken mentioned was that, you know, if you could show that Fano varieties had this volume criterion for ampleness, then their conjecture would be true. So that made me think, okay, is there a way to imitate this example for Fano varieties? And sort of that's what I did. So let's say, can we imitate the Mukai flop for a Fano variety x naught? Okay, so what would that mean? Well, so there's obviously no flop defined on a Fano variety because a flop means you're contracting some curves on which the canonical bundle has degree 0, and by definition a Fano variety has minus k ample. So there aren't going to be any flops directly on the Fano variety. On the other hand, there obviously could be flips. You know, you could have a k negative contraction of some Fano variety, and you would have this flipped variety over there. So let me say what we're trying to do. So it would, you know, so we must look for a flip, not a flop. Okay, so let me say what we're trying to do. So we could seek a picture like the following. So keeping the dimensions the same, we could look for a fivefold mapping to, I don't know, the affine line, let's say, with some special fiber such that x naught, you would like that to be a q factorial terminal Fano. And right. We'd like this to be a flat projective morphism. And we would, let's just be specific about what we want. We can imagine that there's some surface in there, sort of imitating the dimensions here, such that we can contract that surface to a point. Okay. Getting some sort of singular variety z. Okay. So, I mean, I'm writing down the dimensions where I actually managed to find an example, but they are pretty natural given this picture. We could look for a surface in there such that there is a contraction. I mean, you can contract that surface. Sorry, x is contained in this. It's contained in the special fiber. It has dimension 4. But imagine that I can contract that to a point inside this whole fivefold x. Okay, so I would like to imagine that this is a flipping contraction. And I'll say what that means. It just means, so it's a contraction in the sense that it's a surjective mapping with connected fibers. Flipping contraction means that it has relative Picard number equal to 1. So in some sense, you're only contracting one numerical equivalence class of curves, roughly speaking. And flipping, as opposed to flopping, means that the canonical bundle of X has negative degree on the curves that you're contracting. So this is going to be automatic if I've arranged for x naught here to be a Fano variety. Maybe I should make the point that the canonical bundle of the special fiber in this picture, in general, that would be the canonical bundle of x plus x naught restricted to x. But if I'm making a family like this, then the normal bundle of x naught is obviously trivial, so that's just the same thing as kx restricted to x naught. So, the fact that x naught is a Fano variety means that the canonical bundle of x naught is definitely negative on curves in here, and that's equivalent to saying that canonical bundle of x is negative on these curves in here. So in other words, a contraction like that, it's going to be a flipping contraction in this situation. Okay, and then what else do I want? I guess I don't need anything else, because if I can get these properties here, then I know that this flipping contraction possesses a flip. So that means there's some other variety y with certain properties. So by BCHM, I mean any flipping contraction has a flip. The flip sort of x mapping to z exists, and n is unique. So what does that mean? That is, y mapping to z is a k-positive contraction. You're contracting curves in which the canonical bundle of y has positive degree. It also has relative Picard number 1. It's also contracting something of codimension at least 2. So this map is, you could say, iso in codimension 1. You're not contracting any divisors. I guess that's it. Okay, so given this flipping contraction, there always is this flip variety y. It's mapping to z, which I should have said maps to A1. I mean, because I'm contracting something in the special fiber, I still have a map from this map from x to A0 obviously factors through z to A1. And yeah, so y is also sitting on top of A1, and I can define y0 to be the special fiber there. Okay. Right, and there's something there which is getting contracted to this singular point there. Okay. All right. So yeah, so in my example, in general, one might have to think about this for a second, but in my example, T also has dimension 2. You can just look at what this variety is. And in particular, so it happens to have codimension at least 2 in y0 as well as in y. So x0 to y0, I have an obvious birational map from there to there, and that's a modification. It doesn't change anything in codimension 1. Okay. Okay, but then I'm in exactly the same situation as the Mukai flop, and so that sort of automatically says that the volume criterion for ampleness would go wrong for this Fano variety. Let me just explain that if we have all this, then that disproves Haken and de Vernay's question too. So if we had this, then it follows that the Neff cone of this q factorial terminal Fano x0 is not the whole Neff cone of the nearby Fano varieties. Okay, so indeed, why is sort of it's an easy argument. You just so what I need some line bundle that's going to be ample there but not there, and I get it by taking an ample line bundle on, let's say, y. So let L be ample line bundle on y. Right. In particular, it's an ample line bundle on y0. How do I want to say this? Then L is ample on y0, and so it's not ample on x0. As I said, when you make a modification of some variety, something that was ample on the one variety is definitely not ample on the modified variety. But on the other hand, if I have ample line bundle here on Y, it's ample on all, not only on Y naught, but on all these nearby fibers. I mean, I guess maybe clear at this point, but let's see. Okay, but L is ample on Y sub t for t near 0, just because ampleness is an open condition. If you've got a line bundle that's ample on one fiber, then it's open on nearby fibers too. And of course, this rational map from there to there is only changing the central fibers. So that's to say that L corresponding line bundle here is ample on these nearby fibers over there. So since x sub t is the same thing as y sub t, L is ample on x sub t for t near 0. For t near 0, but not equal to 0. Okay, so in other words, I've got a line bundle which, I've got a line bundle on this variety, let's say, which is ample on these other nearby Fano varieties, but it's not ample on x naught. Okay, so that, so in other words, the Neff cone is jumping as you go from x naught to these nearby varieties. So you just have to make the simplest example of a flip like this that you can find, and it's not hard. So in dimension, you start out by guessing what you want the local picture to look like, and then just try to compactify it. I used sort of the simplest flips I could find. A simple flip in dimension, it's going from x to y is a flip of a 5-fold, and it's just, sort of very parallel to the simplest example of a flip which you read and in every book on minimum model theory, the simplest flip of 3 folds. So how do I want to say this? So you start with a flop from the total space of a certain rank 3 vector bundle over P2, mapping to the total space of the same vector bundle over P2. This is sort of the simplest example of a flop between two projective varieties. I guess you can think of this as being, this total space you can think of as being, So this is sort of this total space is something like my x, this is something like my y, and they both map down to some other variety z of dimension 5. Okay, time is short, so I won't write this down. But anyway, the simplest examples of flops have this form where you sort of have a 5-fold in a P2 and you cut it out, glue back in a different way. And then I'll just say divide this out by an action of z mod 2. Divide out by an action in a way where it's not free in codimension 1. It fixes some divisor that sort of changes the canonical bundle in such a way that it turns this flop into a flip. And so that's sort of about the simplest example of a flip you could find. That sort of tells you what you want x to look like locally. You just take this function here to be sort of a general regular function on this variety x naught that's constant on this surface in there. And so that tells you what your family is going to look like locally. You just have to compactify it, make sure that you can get a Fano variety, so that's what I did in my example. Stop there. Okay.